This is our chapter 13 video about colligative properties. So when we say colligative properties, we're talking about the properties that a solution has that makes it different than just the solvent or the solute. So an example would be if we mix together sugar and water and we make sugar water. How is that? What kind of properties does it have that's different than just a beaker of water or just a beaker of sugar? So the difference between these two are the colligative properties. When we make a solution, the properties that solution has are similar to pure solvents. So sugar water is similar to just plain water, but there are going to be some kind of important differences that we'll go over in this video. Those differences are called the colligative properties. And what's interesting about colligative properties is that the colligative properties depend on the concentration of the dissolved solute. So in our sugar water example, it depends on the concentration of the sugar, but it doesn't actually depend on the exact molecular structure of the sugar. And we'll talk about why that's true. The colligative properties that we're going to talk about are the fact that the volumes are non-additive. We're going to talk about freezing point depression, and we're going to talk about boiling point elevation, and then we're going to talk about how colligative properties influence osmosis. So let's talk about the part where volumes are non-additive, and let's look at this picture that we have here. So the caption says that we have 50 milliliters of ethanol and 50 milliliters of water. So I'm going to look at these two volumetric flasks here. I'm going to label one ethanol and the other one water. And volumetric flasks have one value marked on them, so they have one graduation. And you can see when the meniscus is right on that line, we know that they are the volume that's written on the flask. So volumetric flasks are only good for measuring out one volume. And we can see in this picture here that we have 50 milliliters of the ethanol and we have 50 milliliters of the water. So when we add these two things together, we add 50 milliliters of ethanol and we add 50 milliliters of water, and we put them in a larger volumetric flask here. We expect them, 50 and 50, should add up to be 100, but if we look at where the line is there, we can see that the meniscus did not reach the line, and there's some volume missing. So maybe this is about 95 milliliters, it just isn't 100. So how can it be that when we add 50 and 50 milliliters, they don't equal 100, they equal something less, like 95 milliliters. So we'll figure out how that's possible, but I do also want to remind you that, so when we say that volumes are non-additive, it means that this situation is happening. If something says that volumes are additive, it means that when you add 50 and 50, you're going to get 100. So to explain why volumes could be non-additive, let's look at these things here. So we have some marbles and we have some golf balls. I'm going to label these. These are like our ethanols. Ethanol is actually a carbon chain. So it has hydrogens around the outside like this. And then it has an OH group on the end. So those are the bigger molecules. So that's why I'm going to say the golf balls are like the ethanol. And I'm going to say these marbles are like our waters. When we add these together, what happens is the small molecules fit between the empty space between the big molecules. So even though we've added two volumes together, overall, they don't take up any more space because of all that empty volume between the big molecules. So sometimes when the volumes of two different liquids are combined, the volumes are non-additive. And this happens most when the two molecules have a very different size. When the molecules have about the same size, they tend to be additive. One can't fit between each other. It also happens when there are very strong intermolecular forces between the molecules. In this case, we had water, okay? And water can do hydrogen bonding because it has a hydrogen bonded to an electronegative atom with a lone pair. But if you look at ethanol, it can also do hydrogen bonding. So water and ethanol are very attracted to each other, and they have very different sizes. And so that's why the fact that the volumes are not additive is kind of really obvious. Sometimes the difference between them is not so big. So if you add 50 milliliters and 50 milliliters, even if your volumes are non-additive, maybe you get something like 99.5 milliliters and nobody notices. But between ethanol and water, the difference is pretty big. All right, when we talk about our other colligative properties, we're going to be talking about how the freezing point is lowered. We call that freezing point depression because it's going down. And we're also going to talk about boiling point going up. We call that boiling point elevation. And these colligative properties don't really depend on exactly what is added to this solvent. So we'll talk about adding ionic compounds and covalent compounds. It doesn't really matter the molar mass or anything like that. What matters is when you put the solute into the solvent, how many particles are added. That's the thing that changes the properties of the solution the most. So, for example, if we put in a mole of covalent compound, like sugar, that would change the boiling point just as much as if we put in just 1 mole of ions. So it's the 1 mole that determines how the properties change, not necessarily the exact identity of what the mole is. We're going to do some calculations to figure out how boiling point is elevated and freezing point is depressed. And I also kind of wanted to look at a phase diagram to show you how the vapor pressure is also changed. All right, a little review of phase diagrams. A phase diagram has pressure on one axis and temperature on the other, and it gives regions of physical state. So this is the solid region, this is the liquid region, and all down here is the gas region. So it gives us kind of regions of, or data sets of pressure and temperature in which our substance will be a specific physical state. The other thing that phase diagrams tell us is the normal boiling point and the normal freezing point. So if we draw a line across at 1 atmosphere on a phase diagram, and I know there aren't any units on this side, so we're just kind of drawing a line there to represent 1 atmosphere. But if we draw that line across, where the line hits the vapor pressure curve, that's what we call the boiling point. And where it hits the fusion curve, that's what we call the freezing point. So let's focus in on just a pure solvent. So we'll say something like water. Okay, so water is just our pure solvent, and its curves are right here. You can follow those along. They're the blue ones. Okay. So some names we put on these curves is this is the sublimation curve. Okay. This is the vapor pressure curve. And this one here is called the fusion curve. Something that isn't real important to our conversation here, but a point that we learned about is this point that meets all of them. That's called the triple point. So now let's draw our line at 1 atmosphere across. So where it hits the fusion curve, we go down. That temperature right there is the normal freezing point. That's also the normal melting point. So freezing and melting are just opposite processes there. The melting temperature and the freezing temperature are the same number. Okay, if we continue across and we do it where it hits the vapor pressure curve and we go down, that's what we call the normal boiling point. Now, if our substance was water, this would be 0 degrees C, and this would be 100 degrees C. So now let's talk about what happens for a solution. So a solution is made out of a solvent, and then we have to also add a solute there. I'm just going to say something like sugar again. So when we make that solution, what happens to the phase diagram is the fusion curve moves to a lower temperature, and the vapor pressure curve moves to a higher temperature. So they kind of get spread. So if we look at where that 1 atmosphere line hits, if we hit the solution vapor pressure curve and we go down, you can see that the melting point and the freezing point got lower. And if we continue across to the vapor pressure curve and come down, you can see that the boiling point got higher. And so the overall effect is that when we make a solution, the boiling point goes up and the freezing point goes down. We call that elevation and depression. Now, how much it goes up or goes down, so how big we deviate from the normal boiling point or freezing point, is dependent on a couple different things. The first one is how many particles of the solute is produced in water. And we'll talk a little bit more about the details there. But if there are more solute particles in water, it's going to have a bigger effect. And I'm using water as the solvent here, but water doesn't have to be the solvent. We can use other solvents too. It's just the most common solvent. Other things that matter are a constant for the solvent. So that's a constant that we would look up. There are Kb constants. Those are boiling point constants. And there are Kfs, which are freezing point constants. So depending on if you're trying to calculate how much the boiling point is going to be affected, you would use a Kb. If you're trying to calculate the freezing point, you would use a Kf. But it's always for the solvent. And then the last thing that affects the boiling point and freezing point is the concentration of the solution in molality. Okay, so that's the little m. And so when I think about these three factors, this one, factor one, that's all about the solute. How does the solute behave? And then when I think about factor 2, that's all about the solvent. And then factor 3 is the ratio of the solute and solvent. So I kind of think about it. Each one of these gets its say, and then when they mix together, they have a molality, and that has an effect also. So let's talk about the numbers. We're going to start calculating some deviations from normal. So how does the new boiling point of the solution deviate from the boiling point of the solvent? How does the freezing point deviate from the freezing point of the solvent? And on this slide, it gives an equation here. And I need to make a correction over here. On my slides, it says freezing point elevation. So it says freezing point elevation. On your slide, that says depression. So that was a mistake. And this, instead of saying boiling point depression, it should say boiling point elevation. So those are only wrong on my slides. They should be fine on yours. So that is what we're calculating in these equations. This delta T freezing, what that's saying is what is the change of the freezing point? And because freezing points are always lower, the mixture is going to be a lower number. This one's going to be a higher number. And so when you calculate this number, this is always going to come out to be a positive number. Anytime we calculate these delta T's, so anytime we calculate these delta T's, they are always going to be a positive value. And you can kind of think about them as the deviations. So these are how much the freezing or the boiling point has changed from what it was before. And we know that those deviations are dependent on these three factors. And I'm going to put the variable next to each one of these. The number of particles that the compound produces in the solvent. And remember, I'm putting water here because water is our typical solvent, but it doesn't have to be. So I'll just put solvent here. But the number of particles that the compound produces, that's called the factor I. It's technically called the Van't Hoff factor. And we'll figure out how to determine that for a compound, but for right now we're just going to call the number of particles I. And we can see that in the equation here. The constant for the solvent, so if you're calculating the change in boiling point, it'd be the Kb. If you're calculating the change in freezing point, it'd be the Kf. That again comes from a table here. And we can see there's the K in the equation right there. And then the concentration of the solution in molality, that's going to be the M. So the molality is this M in the equation right there. All right, a little more details about that I, the Van't Hoff factor. Again, that represents the number of particles a compound is going to produce when it dissolves in the solvent. And to think about how many particles something will produce, we have to decide whether the compound is a non-electrolyte, a strong electrolyte, or a weak electrolyte. And we can determine whether a compound is a strong, non, or weak electrolyte by using an electrolytes table. Right. I wanted to show some examples of finding the I, the Van't Hoff factor. So I've picked some compounds to use for an example, and we're going to go through each one of these. The decisions that we have to make is we have to decide what type of compound it is. So is it ionic? Is it covalent? Is it an acid? Things like that. Then we're going to decide if the compound is a strong, weak, or non-electrolyte, and we'll use the electrolytes table to do that. And then if it's a strong electrolyte, we decide what it's going to break into, and then we can find the theoretical I, so what we think the I should be. So let's answer each one of these. So for calcium chloride is a metal plus a non-metal. So it is a ionic compound. And this is acetic acid. I can identify it as an acid because it has a hydrogen out front. So this is acetic acid. It's an acid. So technically it's covalent, but it's a special category of covalent compounds that's an acid. Covalent just means that it's all non-metals. So it is covalent, but it's a special kind of covalent. It's an acid, and that's going to be important for us when we use the electrolytes table. And then this molecule here is glucose. It doesn't matter if you knew that was glucose or not. You can see that it is all non-metals. All non-metals means that this is a covalent compound. The next step is to decide if our compound is a strong, weak, or non-electrolyte. So to do this, you're going to use the electrolytes table that we have in our course pack. And the electrolytes table is divided into 3 categories. It has acids, bases, and then it has ionic compounds. So we have 2 of these. We have a compound that's an acid, so we'll use that category to figure out if our acid is a strong or weak or non-electrolyte. We also have an ionic compound, but this covalent compound doesn't even make it to the it doesn't even make it to the electrolytes table. Any covalent compounds are automatically non-electrolytes. The only exceptions are our acids that have their own category. So if it's not an acid, a base, or an ionic compound, it is automatically a non-electrolyte. So I'm going to write that here. So this one is a non-electrolyte. For these other compounds, for our calcium chloride, we would use the ionic side of our electrolytes table. And what it would tell you there is that anything that is a soluble ionic compound, which calcium chloride is a strong electrolyte. So because calcium chloride is ionic, and we can use our solubility tables to figure out that it's soluble, it is a strong electrolyte. All right, the one that we have left is our acid, so we would use the acid category, and that's broken up into 3 subcategories. There are the strong acids, and there are only 6 of them listed here. We don't have any many insoluble acids, so we don't have really many in that category most of the time. But here, for the weak acids, it says all other soluble acids. All right, and so our acetic acid is a soluble acid, so it's going to be a weak electrolyte. All right, if that seemed really confusing or you didn't understand what was going on there, if you didn't understand how to determine something as a strong, weak, or non-electrolyte by using an electrolytes table, you're going to want to pause here and you're going to want to review solubility rules and how to use an electrolytes table. The place that we did that the most was when we did net ionic equations. So if you want to pause and do some work on net ionic equations, or just review the part where we determined whether things were strong, weak, or non-electrolytes, that kind of work is the kind of work that we're going to need to be able to do to continue on with this problem. All right, so assuming that we're okay identifying strong, weak, and non-electrolytes, we're going to continue on. The next thing that we need to do is we need to decide when it becomes soluble, when we mix it into a solvent, what does it break into? And this depends on what type of electrolyte it is. If it's a strong electrolyte, the definition of a strong electrolyte is something that produces ions. So calcium chloride is a strong electrolyte. When we put it into solution, it breaks apart into its ions, calcium ions, and then it also breaks apart into 2 chloride ions. Remember, it doesn't break apart into something like this. It doesn't make a diatomic. The 2 negatives aren't going to want to stick to each other, so it makes 2 separate chloride ions. So this is what it breaks apart into: calcium and 2 chloride ions. If we have a weak electrolyte, the definition of a weak electrolyte is something that only minimally ionizes. So that means that if you put one of these in water, not many of them are actually going to produce ions. And so for weak and non-electrolytes, it doesn't break apart into anything, theoretically. It just stays as whole molecules. So when it becomes soluble, it becomes soluble as whole molecules. And that's the same thing for any non-electrolyte, any covalent compound. It's also going to stay as whole molecules. All right, and then we are on the last step. We are my favorite part, which is finding the Van 't Hoff factor. This part is really easy once you've done all this other work. The Van 't Hoff factor is just how many particles your compound created when it dissolved into water. So here, for calcium chloride, it made 1, 2, 3. It made 3 particles, so 3 is the Van 't Hoff factor. Again, it's 1 calcium and 2 chlorines. That's 3 total particles. So the Van 't Hoff factor is 3. All right, let's continue on to our acetic acid. So acetic acid starts as a molecule. It only produces 1 particle for every molecule, so its Van 't Hoff factor is 1. And same thing with our glucose. It only produces 1 particle for every 1 molecule, so its Van 't Hoff factor is also 1. So the Van 't Hoff factor is just the number of particles the compound creates in solution per unit that you put in. For ionic compounds that are strong electrolytes, it's the number of ions. But for anything that's a weak or non-electrolyte, those theoretically do not break apart at 1, and so for weak and non-electrolytes, the theoretical Van Hoff factor is 1. So when we're finding Van Hoff factors, we usually find a theoretical. It's, for every calcium chloride theoretically breaks apart into 3 things. But what that's assuming is that every calcium chloride ever always breaks totally apart. And statistically, that's close to true, but that's not exactly true. For every, say, 1,000 calcium chlorides, what happens when you put them in water is about 999 of them break apart into calcium ions and chloride ions. But then there's one, that is just going to tough it out. It stays as a calcium chloride. So theoretically, they should all be a Van Hoff factor of 3. But since we have those holdouts once in a while, the real Van Hoff factor is usually a little bit less than 3. So it's something like 2.98, something like that. So we usually, when we're doing problems, we use a theoretical Van Hoff factor, but if we measure it in real life, we know that the Van Hoff factor is going to be just a little bit below what we think it should be. Now, the same type of reasoning actually happens with weak electrolytes. So this is acetic acid. This was our weak electrolyte example. And for weak electrolytes, if we do the same kind of thing, say we have 1,000 acetic acids, and about 999 of them stay as molecules, but one breaks apart into hydrogen ions and acetate ions. Okay. So theoretically, we say that the Van Hoff factor is 1. None of them should break apart. We just get 1 molecule for every 1 molecule we put in. But because some statistically break apart, the Van Hoff factor is actually just a little bit higher than 1. So maybe something like 1.01 or 1.02. The real Van Hoff factor for weak electrolytes is just a little bit higher than 1. Now that we know a little bit more about the Van Hoff factor and how to find it, I want to get back to the types of problems we were trying to do. We were going to use that Van Hoff factor so that we could find how the freezing point or boiling point had changed for a solution compared to the solvent. And let's review what each one of these means. So the delta T, that's the deviation from normal. So that's the change in the freezing point or boiling point. I is the Van Hoff factor, which is the number of particles the solute makes. So that the Van Hoff factor is all about the solute. This K is a constant for the solvent, and we use a KB when we're trying to find boiling point. We use a KF when we're trying to find freezing point. And then this M is the molality of the solution. So that's the ratio of solvent and solute. So I just wanted to kind of talk through a problem without putting any, big numbers in or actually calculating anything. If we're trying to figure out how the boiling point changes when sodium chloride is added to water, I want to look at what that information can tell us about what we would put into this equation here. So we know that we're looking for how the boiling point is going to change, so we are trying to find that deviation from the normal boiling point. So we're trying to find delta T. We know that our compound is sodium chloride. Sodium chloride is going to allow us to calculate the Van't Hoff factor. So the I is always for the solute, and the solute is what's being added to the solvent. Okay, so the sodium chloride is going to allow us to calculate the Van't Hoff factor. Water is our solvent, so we need to look up the K for water. And then the molality, we would need to know what the ratio of sodium chloride to water is. So we would actually need to know like some numbers, some grams of sodium chloride, some kilograms of water, something like that. And we could calculate the molality. And once we had those things, we could calculate how the boiling point had changed. And another little reminder, when we add a solute to a solvent, the boiling point is going to go up, so that's called elevation again. And so the delta T that you get there is going to be a number. I'm just going to say, if you calculate a delta T of 0.5, that means that the solution boiling point is 0.5 degrees higher than the solvent. Okay, so the delta T that you calculate should be added to the boiling point of the regular pure solvent. If you're talking about freezing points are going to go down, and we call that depression. And so when you calculate a delta T, say we did a problem and we calculated a delta T, again, that delta T, it means the solution has a has a freezing point that is 0.5 degrees lower, because freezing points get depressed, so it's lower than the solvent. So if you were doing a freezing point depression problem and you calculated a delta T of 0.05, you would take the freezing point and you would subtract that 0.05 to find the new freezing point of the solution. So let's actually put some numbers in here. I'm looking at this problem, and there are just so many words. I want to remind you that anytime you're looking at a word problem, just reading through and identifying the information is the first step. So when it says this, I'm underlining, calculate the freezing point depression. Okay, so I'm trying to find a delta T. And I'm going to try and find the new freezing point. So once I find the freezing point depression, I can subtract that from the normal freezing point of my solvent, and I can find that new freezing point. Okay, and I'm working with 5 grams of dichlorobenzene, which is a non-electrolyte. Okay, so that right there is telling me the fact that it's a non-electrolyte tells me that the I is 1. Right? It doesn't make any ions in solution. For every one of these dichlorobenzenes I put in solution, I get one particle, one dichlorobenzene. All right, it has a molar mass of this. I'm adding it to 500 grams of carbon tetrachloride. And I'm just looking at the two ratios there. I have 5 grams of one and 500 grams of the other. What that tells me is that this is the solute, and the one that there's more of is the solvent. So that carbon tetrachloride is my solvent. Okay, we have the normal freezing point of carbon tetrachloride is this, and it has the Kf, so that's the freezing point constant right there. Okay, so I cleaned it up a little bit, but I left the information, like we're trying to find the delta T, we have our solute, we have our solvent, things like that. Okay, the equation that we're going to use is delta T equals I times K times M. And we already have some of these things. We talked about how since it's a non-electrolyte, we know the I is going to be 1. The K is for the solvent. Our solvent is the carbon tetrachloride, and the problem tells us that the K is this. All right, so I already have 2 of them. The only one that's left is my molality. So I need to calculate molality, and then I'm going to put it into this equation, and I can find my delta T. All right, we're going to practice our concentration calculations. Remember, molality is moles of solute divided by kilograms of solvent. So in this case, it's going to be moles of dichlorobenzene. I'm just going to abbreviate that DCB. And then kilograms of carbon tetrachloride on the bottom. All right, so we need to find moles of dichlorobenzene first. It tells me that I have 500 grams and that the molar mass is 147. So, not 500 grams, 5 grams, and the molar mass is 147 grams per mole. So I got 0.0340 moles, and there was a 1 past that. And then to find kilograms of carbon tetrachloride, I'm going to say there were 500 grams. 500 grams, there are 1,000 grams in 1 kilogram, so that's 0.5 kilograms carbon tetrachloride. Now when I divide the moles by the kilograms to find molality, I got that for the molality is equal to 0.68027, and there should only be 3 sig figs there, so I'm going to underline it there. All right, and that is my molality. I just have to put that right in here. And it shouldn't be this, I accidentally didn't put a 0 in there, so 0.68027. All right, so now we're going to put that in there. And I got that delta T is equal to 1 times 29.9 times 0.068027 with 3 sig figs. And when I calculated that the deviation from normal was 2.03 degrees Celsius. All right, so the change in freezing point is 2.03 degrees Celsius. We have been able to find our change, but now we want to find what the new freezing point is. And I cleaned things up a little bit, and I left my value there. So the freezing point has changed 2.3%, and we know that freezing points are always lower when it's a solution than the freezing point of the solvent. So if we look at the number for the solvent, and I'm thinking about a thermometer here, so this is negative 21, this is negative 22, this is negative 22.9. That is the normal freezing point for carbon tetrachloride. What this calculation here is telling us is that the freezing point has gone down another 2.03 degrees Celsius. So what we're trying to do is find that new freezing point. So what we should do is we should take the freezing point and we're going to subtract another 203. So negative 22.9 minus 2.03 degrees. And on my calculator I got negative 24.9, only one place past the decimal, degrees Celsius. So that new freezing point is 2.3 degrees lower than the normal freezing point. Our problem said to calculate the freezing point depression, and we did that. And it also said to calculate the new freezing point, and now we've done that here. So the new freezing point is negative 24.9. Here's another type of problem. It tells you that we have so many grams of a molecular compound that's a non-electrolyte. Remember, that tells us automatically that the I is 1. It's added to 150 grams of water. And I'm just looking at those relative numbers there. It tells me that because there's less of this, it's the solute, and there's more of this, it's the solvent. Okay. The new freezing point is negative 1.3 degrees C. So the new freezing point, that tells us how much it's deviated from the old. And it says water's Kf is this. Calculate the molar mass of this compound. All right, so to kind of focus us, we are trying to find molar mass. Molar mass is going to be it's going to be grams of the compound divided by moles of the compound. And let's look at what we have in our problem and see if we are anywhere close to this. In the problem, it says that we have so many grams of the compound. That's already the top part. So it looks like we need to focus on finding this moles of the compound, and then we can take the grams and we can divide by the moles and we can get the molar mass. We can only do that if we first find the moles of the compound here. All right, so to find that moles of compound, I'm just going to look for other things in my problem and kind of try and relate this. It gives me like a delta T, it gives me a Kf, things like that. And so it seems like I'm going to use the only equation I know that has to do with colligative properties and temperature. Delta T equals I times K times M. And when I look at that, I realize, okay, well, it tells me information so that I could find a delta T. It tells me an I, so I could find this. It tells me an F, so I could do this. I should be able to solve for molality. Molality is moles per kilogram of solvent. That has moles in it. That means that I should be able to get to moles of my compound. And so let's do it that way. The first thing I'm going to do is I'm going to rearrange this. I'm trying to find molality, so I'm going to rearrange the equation so that it's really nice. And then I'm going to try and figure out where I can put in these numbers. Okay, so we already have the I, so we got that one. We have the Kf, so we have that one. What we need to do is find the change in temperature. And it tells us that the new freezing point is 1.3 degrees. So if water normally freezes at 0 degrees Celsius, and you might know that for water, I wouldn't expect you to know that for many other solvents. Like nobody knows, the freezing point of carbon tetrachloride off the top of their head. Water, you might not actually know this, but there are charts of freezing points and boiling points and the Ks that go with them, usually associated with problems like this. So we might know water off the top of our head. We'll just pretend that we did. And if it was a different solvent, we would have had to look it up. So water freezes at 0, and it's telling us that the new freezing point is negative 1.3 degrees. So the difference between those is the delta T. So the delta T is 1.3 degrees. Now, a lot of people like to think of the delta T as like an absolute value. It's always a positive number. That's true. It doesn't take into consideration whether it's a freezing point depression like we have here or a boiling point elevation. But we have our delta T, so we can put that in here. All right, so now putting in the numbers, 1.3 degrees C. My Van 't Hoff factor was 1 because it's a non-electrolyte, and my K was 1.86. The units are degrees C per molality. And so when you do the units there, when you divide degrees C by degrees C, those cancel out and you get 1 over molality, which is the inverse of the inverse is molality. On my calculator, I got 0.6989 for molality. Looks like it only should have 2 sig figs. All right, I've got molality, but how do I get to moles of compound? If we look closely at the units of molality, that would be moles of our unknown, our solute, divided by kilograms of solvent. Okay, so if we multiply this by kilograms of solvent, we'll get just the moles of the unknown. So I like to set that up in a very dimensional analysis type way. My problem said that I had 150 grams of water. Water's my solvent here. And for every kilogram, for every 1,000 grams of water, I have 1 kilogram. And the molality says that for every 1 kilogram of water, I have 0.6989 moles of unknown. So the way the units work out there, grams of water, cancel with grams of water, kilograms with kilograms, and I just get moles of unknown, which is what I wanted. And for a number, for my moles of unknown, I got 0.1048, and it should only have 2 sig figs because that only had 2 sig figs. So I have my moles of unknown, I have my grams of unknown from the problem. Now I can calculate my molar mass. So the molar mass is going to be grams, 35.9 grams of unknown divided by 0.1048 moles of unknown. And when I did that on my calculator, I got that the molar mass was equal to 342.4 to 2 sig figs. That would be 340 grams per mole. That's a really big molecule. It's probably something like a protein or something like that. So that's some pretty interesting information there. You can actually calculate the molar mass of a compound by weighing some out, adding it to a certain amount of solid, and figuring out how much the temperature, how much the freezing point goes down. So by measuring freezing point depression, we can find a molar mass, and molar mass tells us a lot about a compound. So for example, we know that this compound is not a pure element because all of our elements are less than this mass. We know that it's a molecule, we know that it's a pretty big molecule. All right, let's do one more practice calculation. This problem says that the freezing point of an aqueous, okay, that word aqueous means that it's in water. So water is our solvent there. So it's an aqueous solution, and it gives us the molality. It says it's calcium chloride, and it says that that is the freezing point. What is the Van't Hoff factor? All right, so I'm going to use my equation, I times K times M, and it tells us information so that we can find the change in temperature. It tells us the molality. We know the K from the problem that we just did. K for water is 1.86 degrees Celsius per molality. That's not a number that you would know off the top of your head. You would use a chart to look that one up, but we just had it in our last problem, so I knew it from that. So it looks like we have the delta T, we have the K, we have the M. Let's calculate that I. The first thing that I'm going to do is I'm just going to rearrange this equation so that I get the I by itself on one side. K and M is I. And now I'm going to start putting my numbers in. So 1.86 degrees C per molality was my K. 0.050 molality was my molality. And for the delta T, again, water has a freezing point of 0. This freezing point is negative 0.27. So it's gone down. It's been depressed 0.27 degrees. 0.27 is my delta T. So when I put those numbers in, I get 2.903 for my I. Just a little reflection there. Does that make sense for calcium chloride? Okay, what do we think it should be? Well, calcium chloride is a strong electrolyte. I know that because it's an ionic compound and it's soluble. And strong electrolytes break apart into ions. So calcium chloride breaks apart into calcium and 2 chloride ions. So I would think one of these and 2 of those I would think that the Van Hoff factor should be 3. We calculated that it was 2.9. That's what we were talking about. When we do it like this, we're talking about a theoretical value, what would happen if every calcium chloride behaved exactly as it should. But in reality, when we do a measurement and we find something experimentally, we use the empirical method, we usually calculate that the I's for ionic compounds are lower than the theoretical. And that's normal. That's just telling us that every calcium chloride out there doesn't break apart, or every calcium chloride in this experiment doesn't break apart into 1 calcium and 2 chlorides. Some of them stay together as calcium chloride compounds. All right. The rest of chapter 13 is not so mathy. It's a lot more kind of concept. And it finishes up by talking about osmosis. So osmosis is something that you might have heard of before. You might know that it's like a natural procedure, but you might not know what it is. So I thought I'd go through the process of just describing what an osmosis situation is. All right. Osmosis is a situation where you have 2 solutions and they have different concentrations. So you have one that is a higher concentration and one that is a lower concentration. They are separated by a semi-permeable membrane. So let's break that apart. Semi-permeable. Semi-permeable means that it is a surface, or it's a kind of a line where some things can make it through and other things can't. So the fact that it's a membrane tells us that it is blocking the 2 solutions from each other, but it has holes in it. And so whatever is smaller than those holes, like these water molecules, can make it through the semi-permeable membrane. It's semi-permeable because these big things can't make it through. So it's what we call a size exclusion permeable membrane. It excludes things based on their size. Now you might think this is a really specific situation and where does this really happen? But where this happens is, I'm just going to kind of mark up our picture here. We have a high concentration on this side. We have a low concentration on this side. And I'm talking about the concentration of whatever these green molecules or particles are here. There are some on this side, so it's a high concentration. There aren't any on this side, so it's a very low concentration. It's like a 0 concentration. So where this happens in nature is cell walls. So cell walls are semi-permeable membranes. They allow some things to go past and other things they keep out. And so cell walls and things like plant membranes all work on the osmosis principle. They have like nutrients, they have plasma, if it's blood, things like that. So if it's our skin, we have a higher concentration on one side of our skin and we have no plasma on the other side of our skin. So almost all biological situations work in an osmosis situation where you have 2 different concentrations blocked, separated from each other by a semi-permeable membrane. Sometimes the semi-permeable membrane is skin, sometimes it's just a cell wall, sometimes it's a plant membrane, but there's a lot of semi-permeable membranes out there. Kind of in the science realm, you can actually buy semi-permeable membranes. There's whole catalogs of them. They look kind of like saran wrap. They look kind of plasticky. They feel like saran wrap, but there's different kinds of semi-permeable membranes. Some are size exclusion, and so there's catalogs where you can literally look up how big you want the holes in the membrane to be and how big you want your membrane to be. So do you want it to be like 1 inch wide? Do you want it to be a strip that's 10 inches long? Things like that. You can buy them in all different sorts. You can also buy semi-permeable membranes that allow certain charges to go across them and kind of exclude other charges. So there's all kinds of these things out there that we've developed, but there are a lot of biological ones too. Now that's the osmosis situation, but what is the process of osmosis? Okay, so I want to focus on this picture now, and it's just a slightly different version of this picture that we were talking about. What we have here is we have our semi-permeable membrane right here, and it's separating out pure water, which is the low concentration, from something like a solution that actually has particles in it. So this is the higher concentration. And this is a solution. Now there's something about this picture that I don't like. This should not say solvent particles. It should say solute particles. Okay, because water is our solvent here. Whatever these blue things are our solutes. And so in this situation, we're setting up an osmosis process. What happens in osmosis is that the solutions will try and even out the concentrations by passing through the membrane. So these two concentrations, or these two solutions, want to be at the same concentration, and they'll try and mix together as much as possible to make that happen. If we took out the semi-permeable membrane, they would just mix together and they would have the exact same concentration. But that semi-permeable membrane keeps them from mixing. And that semi-permeable membrane allows water only to go back and forth between them. It doesn't allow the solute particles. The solute particles are just too big to make it across the membrane. So if they're trying to even out the concentrations, and the easiest way would be to get solute particles on this side, but that's not going to happen. The only other way is to take waters from this side and get them through this semi-permeable membrane to this side. And so over time, if we keep on putting waters and we keep on doing that, over on this side, it's going to become more dilute. And it's going to start to be close to the low concentration on this side. So when it dilutes, when the waters come to this side and dilute out the solute particles, the concentrations start to be closer to each other. And that's the process of osmosis. The process of osmosis is moving a solvent across a semi-permeable membrane so that it starts to even out the concentrations. And this is actually how plants absorb water from the soil. So their roots are a semi-permeable membrane. They have solute particles on this side, and water moves from the ground into the roots to try and dilute out these solute particles, but it can never totally dilute them. So osmosis is a way to keep on moving water or a solvent across a semi-permeable membrane kind of until we run out of water. So it'll keep on doing this, it'll keep on moving water, it'll never totally dilute out the solute particles, so it just keeps on moving until we run out of water. And that's kind of the situation that's happened up here. So this was the picture that we were working with before, where we have solute particles on this side. And the waters started coming into the more concentrated side to dilute it out. And when that happens, so now on this side, we have more volume. You can see that the volume went up quite a bit, and the volume on this side went down because all those waters are moving to this side. So that'll keep on happening until we run out of waters on this side. Or another thing that happens is if this is a closed system. So imagine that this is a root to a plant here. And this is the soil with water in it. Water will keep on moving into the root until the root fills up. When it reaches a high enough pressure inside the root, it stops the waters from moving. So when this is totally full, when the root is totally full, the osmotic process stops. There isn't any more room for water. And we call that, when this side is full, we call that reaching the osmotic pressure. When we've reached the osmotic pressure, osmosis stops. And that's what brings me to something you might have heard about, which is called reverse osmosis. Okay, so reverse osmosis would be if we can get the waters not to move according to osmosis, so that would be to the more concentrated side. Reverse osmosis would be if we could get waters to move to the less concentrated side. And how we do that, how we do reverse osmosis, is you take a solution, like this one, you have a semi-permeable membrane, and you basically just push down on it. You increase the osmotic pressure a lot. So you're just putting a lot of pressure on this side. And what happens is the water molecules squeeze out the permeable membrane, the semi-permeable membrane. The solute particles can't make it through the membrane. And basically what you're doing here is you're using that semi-permeable membrane is like a strainer. You're pushing down and you're letting the waters fall out, and you're collecting all the solute particles on this side. It's basically just a little mini version of a colander there. So when we do reverse osmosis, we apply a pressure greater than the osmotic pressure, and at that point the membrane just serves as a filter. When we do this in kind of science in real life, reverse osmosis looks something like this. And what's happening there is they are taking seawater and they're pumping it into a tank. They put it up against a semi-permeable membrane, okay? And then they apply a great pressure to this, and it pushes down on this solution, and the water molecules go through the semi-permeable membrane and they filter out the fresh water. What's left in this is a really concentrated brine solution, and they pump this out. And they do that again and again, and that's the way they can filter fresh water from seawater. So they can use reverse osmosis for water desalination. So in this video, we talked about colligative properties, we talked about the definition of colligative properties, and we talked about three main colligative properties. The fact that the volumes can be non-additive, the fact that boiling points get elevated, and freezing points get depressed when you add a solid to a solvent to make a solution. Now, when we were doing the calculations for boiling point elevation and freezing point depression, we needed to be able to identify electrolytes and do things like calculate the molality so that we could do those calculations. Then we finished up by talking about osmosis. Now, if you'd like some practice with these calculations, like these calculations here, you can go to our course pack, and on page 79, page 81, and page 83, there are some worksheets called Colligative Properties. And there's a Colligative Properties A, B, and C. So 3 different worksheets that you can practice with. So I think this is our last video of the semester, and I would make another chemistry joke, but all the good ones are gone, okay? So cheesy, but I miss you guys.